Hello everyone, welcome to the channel. Today we are gonna see that if n is a perfect square of a positive integer, then n mod 4, that is the remainder of n when divided by 4, will be either 0 or 1. So in one way we can say that n is kind of stationary with respect to 4. Now this is a property, a small observation from number theory. And to begin with this, we can like just look at examples to start with to get an idea of things. I write here the set of perfect squares of positive integers first. That starts with 1, 4, 9, 16, 25, and so on. This goes on till infinity. But the important thing here is that this is a countably infinite set. So I won't get into the details of what is countably infinite and uncountably infinite because that's more mathematical analysis than number theory. But this is the set we are dealing with here. So n, of course, n belongs to this set from the problem. N belongs to this set, so n will be any one element from this set. And if we just directly start looking at the values, say n equals 1, then 1 mod 4 is congruent to 1. This means when 1 is divided by 4, we get a remainder of 1. This triple equals kind of symbol is usually called congruent to. It's a standard function of modular arithmetic. So if n is 2, n equals 2, then 2 mod 4 is congruent to, sorry, n cannot be 2 because n has to belong to this set. I'm dealing with perfect squares. So when n equals 4, 4 mod 4 leaves a remainder of 0. N is 9, 9 mod 4 leaves a remainder of 1, and 16 mod 4 leaves a remainder of 0 again because 16 is divisible by 4. 25 mod 4 leaves a remainder of 1 again. 24 plus 1. So yeah, if we keep on taking exact values, exact numbers of all these sets, then we can see that we are getting either 0 or 1, and that is what we set out with in the beginning. So we can observe that here, but it's not a very formal proof because this is a countable set. Definitely it's countable, but it's countably infinite. So then we're going to have to take infinite values and keep on doing this. So that's of course not a formal definition kind of. So to prove this kind of, we can observe that ones and zeros are repeated alternately here. That's the first observation, that you don't have consecutive ones and consecutive zeros. You always have ones and zeros alternating. So these are the ones and these are the zeros. Okay, ones and zeros alternating. That gives us an idea that whenever something's alternating with a frequency of 2, so it repeats itself for every 2 instance of numbers. So it leaves one number and then the next one is 1, leaves another instance and then it's 1. Whenever there's something that's got to be, we have something that's got something to do with 2, uh, even and odd is the next thing that we usually think of, because you're seeing some kind of repetition of 2, because even and odd is just a number, any number m, positive integer. So m is, so when m is divided by 2, this will always be 0 or 1. M doesn't have to be a perfect square, m is just any number, but it will always be 0 and 1. If it's exactly divisible by 2, it's 0, we call it even, and if it's 1, then we call it odd. That's pretty basic and we know it. Now, how that is relevant here is, even though we are dividing by 4, this kind of gives an idea of something that resembles what we saw with even and odd. So maybe this gives us an idea that this could be related to n being even or odd. So to think a bit more about n, because n is a perfect square, not just any positive integer. There's something very important with perfect square. So perfect square is a very special property that n has, and we are only taking those perfect squares. So since n is a perfect square, it will be possible to write n as the square of another integer, and k has to belong to a positive integer as well, because the root of a perfect square that is a positive integer will have to be a positive integer. If I write it like this, then I'm saying that for every n, since n is a perfect square, for every n I have a corresponding k, where k is defined as some function that I might choose to write like root of n, square root basically. So there will exist k for every n. And now, since I got some idea about even and odd here, and I wouldn't directly be able to apply even and odd to n, um, we are going to apply even and odd concept to k, because k kind of makes up n. If you exactly know k, you will know n. Although the problem is about n, but if you knew k, hypothetically, if we knew k, we know n directly, because n is just the square of it. So then if k is even, because there are only two possibilities as I had shown with m, another arbitrary positive integer. So k is not any different from m, because k is just a positive integer. Whether it's a perfect square or not, we don't know, but n definitely is. So if k is even, then we can write k as 2 times of j, where j is another positive integer. See, you might be thinking we just keep on defining more and more variables, but actually we are not. We are defining properties here. We are defining n, that's a perfect square. From this identity, we define the perfect square property. And from this identity, we define k to be even. So that's another property we are adding. So we are simply just simply just keep on constraining it, because you have an uncountably infinite set. To prove it, you will need to keep on constraining it in some way. I'm constraining by square, and then by even numbers, I'm saying k is even. So if k is even and twice of j, then what is n? Because I started out with n and I brought in k here, but I'm ultimately interested in n. So n is k squared, which is twice of j squared, which is pretty straightforward to see that this is 4 times j squared. It's interesting and important to know that you get j squared here, and I'll probably talk about this later, but for this problem we're interested in this 4. This 4 is exactly what we wanted, because we have 4 here. we were proving something with respect to 4, so we get 4 here, and that means that this mod of 4 will always be congruent to 0, because 4 is directly a factor of this n then if k is even, and so on. So now we are done and we have one element of it proved here. So we can say that if k is even, then n mod 4 is identically 0. This part is done. So intuitively, we might feel that then odd, if k is odd, we should get 1. That's what you feel, but that's what we still need to prove now. And then we would be completely done. So the other case, obviously, we will have to consider is if k is odd, then k can be represented as a number such as +1. But the problem here is I have taken twice j plus 1. When I define it in this way, I will have to write this like is union of this. Not only positive integers, 0 is not a positive integer, but I have to consider the case where 0 is part, like j can be 0, because I need j to be 0 when k is equals 1, because 1, although 1 is neither even or odd technically, in this case I'll group 1 into, I'll call it an odd number just to simplify things, and simply because 1 mod 2 will be 1. So if k is odd, then k squared, then what is n? N is k squared, and this time is this. And as we might know from identities of squares, algebraic identities, this will be 4j squared plus 4j plus 1. Very promising this, because I keep on getting these 4's here and I have 4 here, so whenever I see 4, that's very convenient for us, because I can then directly factorize 4 and write it in this form, plus 1. Once again, this term directly has 4 as a factor, so when we are doing a mod 4 here, this gets exactly divided by 4, so all we are left with is a remainder of 1, so that is 1. And now we are done, we're perfectly done. This is 0 and 1. So in general, we can say that if k is even, then n, that is k squared mod 4, probably I should be writing brackets around the mod to be more consistent, sorry, n, that is k squared mod 4 is congruent to 0, and when k is odd, hey, I'm just summarizing, we're already done, but I'm generalizing. A squared mod 4 gives us 1, and that's identically valid for all positive integers n that are perfect squares belonging to this set. So I don't have to go through the elements one by one. I've proved it in a very general way, and this will always be applicable everywhere. So thank you so much for being with me. Thanks.